And I think I will hand it to Professor James for today's lecture.
So I'm David James. I'm a professor here in electrical and computer engineering. I'm also co-director of our Semiconductor Degrees program and Dean's Faculty Fellow for the overall Semiconductors at Purdue initiative. So my job today is to kind of give you an overview of the course and more an overview of the field, I guess. As Professor Swaby said, we will have a series of industry speakers coming in over the course of the semester. What he should have said was we're going to have a series of industry speakers. I mean, these are heavy hitters that will be coming in. So you have a unique opportunity to learn from some of the leaders in the field, to get their insights. I encourage you to interact, participate, ask them questions, because I think there's a lot of good insights that will come. So one of the things that everybody's paying attention to now is the fact that there's a new CHIPS and Science Act that was passed in 2022. This is really something that should be, I think, recognized as kind of a bipartisan effort. It had really been going on for some time before 2022. It's continuing on now. It had several broad goals. One was to reshore, to bring back into the US semiconductor manufacturing and harden our supply chains. You may recall back during the pandemic where it was really hard to buy things. You couldn't buy a car because we didn't have chips. You couldn't buy various appliances. We didn't have chips. Everything was in short supply because the global supply chain had been disrupted. So one of the goals of this CHIPS and Science Act is to make a more resilient supply chain, but in particular to bring some of that back into the US. This was intended to bolster our strengths in chip design and manufacturing tools, and R means the US, and regain the lead in leading edge technology, and to really accelerate the pace of innovation. So if you learn nothing else from today's lecture or the whole semester, one of the things you need to pay attention to is this is an innovation-driven industry. There's nothing stagnant about it. It's constantly moving, constantly innovating, constantly moving forward. So today, I'm adapting some slides that Professor Mark Lundstrom had developed over the last few years, trying to put a little bit different spin on it. But I want to just remind you about what semiconductors is, or maybe for some of you, introduce you to what semiconductors is. So most of you are familiar with electrical conductors. When you go to plug in your a device into a wall socket, electricity flows through wires. You can then charge your device. That's all pumping electrons around through conductors. We do that with metals. If you plug in, you'll actually be using a cord of some sort, a power cable or cord that has in it probably copper wires. Copper is a good conductive metal. And metals have conductivity on the order of 10 to the 5th to 10 to the 7th inverse ohm centimeters. I'm not using MKS units here. I'm using centimeters, which what the industry actually uses. On the other end of the spectrum, if you do plug in your power cord, you don't want to get a shock from touching bare wires. So you have an insulator. You wrap an insulator around your wires so you don't get shocks. But more in general, we have insulators that can stand off current. And insulators like glass, silicon dioxide, the window glass we have here, or the glass on the side walls of the room here, are basically insulators that have sigmas on the order of 10 to the minus 12. So between 10 to the minus 12 and 10 to the plus 5th is a number of orders of magnitude. It's late in the day, I don't want to try to do that math in my head, but a number of order of magnitude difference between what a conductor and an insulator is in terms of electrical conductivity. Semiconductors sort of sit in that broad range in between. So here's a chunk of some semiconductor material. They tend to be kind of, at least crystalline semiconductors tend to be kind of grayish looking, maybe a little shiny sometimes. It's not always, but sometimes. And a semiconductor has several interesting properties, one of which is that its conductivity can be changed over a large range. Just looking at, say, silicon, which is the predominant semiconductor out there for general purpose electronics, its conductivity can be tuned over about 8 orders of magnitude to be somewhat metallic-like on one end. It doesn't get nearly as insulating as a piece of silicon dioxide at the other end, but you can change its conductivity by a lot. 8 orders of magnitude is a lot. But more importantly, you can change its electronic and optical properties by orders of magnitude by putting in impurities, other small concentrations of other atoms known as impurities or doping. You can apply light. That's what makes a solar cell work, or a photodetector. You can apply an electric field or potential, which is of particular interest to us because you can build a transistor where you put an electric field to change a potential that becomes an electric field where you can change the conductivity of the device. You can make a switch. You can turn it on and off. Like I go to the wall switch here and turn the lights on and off in the room, you'll say, oh, big deal. You know, you had a switch. But we'll see in modern devices, we have transistor devices that can switch a lot, and we can build a lot of them. So there's really a couple different definitions. A semiconductor material is what we just said, but the semiconductor industry or a semiconductor chip kind of means the overall electronics, these circuits and integration that you do. So microelectronics is really kind of the design and manufacture of complete electronic systems on semiconductor chips. We'll talk about what that means in a minute. The basic building block of these systems are transistors. Think of it as just tiny switches, of which we can build a lot, and we can use them to do things like digital logic, analog devices. We actually use comparable devices for lighting, solid-state lighting, for solar cells, lots of things. A leading-edge chip can contain tens of billions of transistors connected with 60 miles or so of wires. That's a lot packed on a small chip. And the industry that does this is broadly known as the semiconductor industry. They do everything from chip design to manufacture to packaging. It includes the tools industry that builds the systems that go into a manufacturing facility. It includes the materials industry. It includes design tools at both ends. So that's the overall semiconductor industry or semiconductor ecosystem. So there's semiconductors almost everywhere. So all of these devices, a modern car has hundreds of integrated circuits in it, hundreds of chips. Your televisions, refrigerators, computer systems, your smartphone that most of us can't do without, there's semiconductor chips in all of those. So it's really a foundational technology for many of the challenges of the 21st century. We think of it as being our electronics we carry with it. It underpins the internet. It underpins things that are happening in agricultural, healthcare, defense, security. It underpins almost everything we do. You've probably read some things about artificial intelligence, read some articles or notes about cybersecurity. It's a huge issue for lots and lots of things we do. So if we want to understand a semiconductor chip, it's useful to go back and kind of look at how we got to where we are, right? So the first electronics area was actually vacuum tubes. Does anybody here actually own a vacuum tube amplifier? Anybody have like a guitar amplifier with vacuum tubes or anything? Any of your parents or grandparents? A couple of people. You got a vacuum tube amplifier for guitar?
Yeah, it's really old.
Do you use it?
Not in a while.
Not in a while. Okay, good. So we did a lot with vacuum tubes. It turns out you could build guitar amplifiers, you could build stereo amplifiers, listen to music on your stereo speakers. We did television. You could build color television with vacuum tubes. We basically went to the moon on vacuum tubes in the first manned space missions. So this all dates back to sort of the 1880s, where people started understanding the basic physical effects. They started understanding how to build a diode and a triode. A diode's a two-terminal electronic device. A triode is a three-terminal electronic device. And so the way a vacuum tube worked is you actually had a hot filament. Think of basically an incandescent light bulb. I know you're all solid-state lighting people, but an incandescent light bulb, remember it had a filament in it, got really hot. Well, think about using that heat to generate a stream of electrons and then controlling the electrons with additional plates and grids and stuff within that. Vacuum tubes worked great. They actually did wonderful things, but they really weren't very miniaturizable. Early computers, if you've ever read about things called like ENIACs and things like that, were actually built out of vacuum tubes. That's what gave rise to the terminology of a bug in a computer program. Anybody ever heard of a bug in a program? That literally related to bugs crawling in, like little, real bugs, insects, crawling into the vacuum tube systems. The vacuum tubes were nice and warm. The bugs would crawl in there, short something out, and you'd have to go in and replace that. So that's where the idea of a bug in a computer originally came from. Not very practical if you wanted to do large-scale electronics. But this actually did allow us to do radio, television. Again, you'd open up the back of a television. There would be a series of vacuum tubes that would plug in. There were, at the local hardware store or drugstore or whatever, they'd have vacuum tube testers. You could literally pull your vacuum tubes out of your television, get on your bike, pedal down to the local hardware store and test all your vacuum tubes. Kind of quaint, it worked, but again, we had television, we had radio, we had lots of things we could do. The very first computers, as I mentioned, were with vacuum tubes. This is an ENIAC from about 1945. You see some of the numbers in the bottom there. 17,000 or so vacuum tubes, weighed 30 tons. And it could do a grand total of 5,000 add, subtract operations per second. Most of you carry more power in a wristwatch nowadays, Fitbit or whatever on your wrist, way more computational power than that. But this was kind of the state of the art when computers first came out. One of the things that really revolutionized electronics was the discovery of the transistor in 1947 by people from Bell Labs. This led to a Nobel Prize. The very first transistor was pretty crude. You see an actual working version of it here on the right. It was huge. I mean, this thing is, centimeters in scale. It's one basically contact that they could make between two pieces of germanium, or a piece of germanium and another contact, I should say. But this let people start thinking about a new technology that could be much more scalable. If you look at some of the early articles about how you might be able to use these new transistors, they were saying, well, maybe you could eventually miniaturize a hearing aid. Instead of carrying a big box with a vacuum tube in it, maybe you could make a hearing aid smaller. But not too many people were really thinking ahead toward what it could really do. It turns out it was a very significant invention. One of the first places it was used was in transistor radios. Anybody have one of these in their grandparents' attic or anything? Anybody run across one of these, an old transistor radio? These had a grand total of like 4 or 6 transistors in them. One of the very first ones was from Texas Instruments that had, I think, 4 transistors. Sony had one that actually kind of got them started, I think, in this broad electronics industry as a 6 transistor, what they called shirt pocket radio. It was actually small enough to slip into your shirt pocket. And it turns out that the very first TI one was actually manufactured in, anybody know what city the first one was? Oh, it's already there. It's manufactured in Indiana. There was a company in Indianapolis who was actually making one of these very first transistor radios. It was a way that Texas Instruments got started with a market for their actual transistors. So how did we get from that idea where in 1954 you could buy a 4 transistor radio for something like $585 in current money, $585 in our 2025 dollars. It was over $100 per transistor. Nowadays, you can buy tens of billions of transistors for that same amount of money. You can go out and buy a smartphone for about that amount of money. I know some of them cost more than that, but for that amount of money, you can buy tens of billions of transistors. So we went in the 1950s from being able to buy 4 transistors to now where we can buy tens of billions. How did we do that? Yes?
We developed the semiconductor industry more. We miniaturized the size of transistors. We also made manufacturing operations through like EUV and
We used EUV. That's how we did it. Did you get the answer? We used EUV. Good. We're setting the stage for another lecture. Exactly. We miniaturized things. We found out how to manufacture them. But what we really did was we made what are known as integrated circuits. So one of the real breakthroughs, the individual transistors were great. They could be made smaller, lower power than vacuum tubes. But that oven by itself wasn't the key breakthrough. Isaac Asimov, you probably heard him as a science fiction writer, but he had a quote saying, "It's probably the most important moment since mankind emerged as a life form." That's quite a quote, but let's see if we kind of believe some of that happened. So he was really talking about the planar process which we use to manufacture integrated circuits. But the first question is, what's an integrated circuit? So there's several different versions of who invented the first integrated circuit. This one says Fairchild. Texas Instruments also kind of claims that they had the first integrated circuit. But what it really was a chance to start putting multiple transistors together on the same chip, the same small piece of semiconductor. Robert Noyce from Fairchild and Jack Kilby from Texas Instruments, both sort of about the same time, developed integrated circuits. At the time, it was just a few. It was 2 or 3 transistors on a chip, maybe 4. But what it allowed them to do is then start putting together several transistors printing on a chip. So you see a sketch or a photograph here of actually a simple integrated circuit. This is basically a NOR gate from the computer that controlled the Apollo spacecraft. So this is what we went to the moon on, was a simple, very simple circuit like this, simple logic circuit. But you can see on there already, we're actually printing things on a piece of germanium or silicon. And people knew how to do printing. We'd been printing books for a long time. That basic idea of printing was around. So it was a technology that could be used and adapted. But this idea of having multiple transistors on a chip where they're already interconnected by how you print it on the chip. So you could get the devices defined, you could also interconnect them. The integrated circuit was a real breakthrough. So the very first silicon MOSFET was around 1960. Here's a cross-section. MOSFET stands for metal oxide semiconductor field effect transistor. And I know there's a lot of stuff to unpack there, but it's telling us two things, and it helps us think ahead. Because in this field, acronyms are everything. If you can decode the acronym, it's probably pretty descriptive. Let's look through this one for a minute. It's a transistor. Transistor is a switch. You can switch it on and off electrically. It's a field effect transistor, which tells us something about the physics of how it works. And it's a metal oxide semiconductor device, which tells us we're going to have a metal, we're going to have an oxide, and we're going to have a semiconductor. Well, we already saw those a couple slides ago. We know what that all is. So here's the basic cross-section. There's a kind of a black, I don't know if you can see this. There's kind of this black rectangle up here that's actually the gate region. There's a thin oxide layer here, and then the silicon down here. There'll be a channel that will form here. There's a region called the source, the region called the drain. Again, terminology helps us out here because what's going to happen is some kind of electronic charge is going to go from the source to the drain. It's going to be controlled by the gates. We have a way to control a current flow from a source to a drain through a gate. Let's not worry about signs and all that kind of stuff. We just need to understand that, right? So we can see that metal oxide semiconductor, in this case silicon, metal oxide silicon device structure. Okay. So it really works. By the way, a Purdue alum, John Atala, played a key role in developing the first MOSFET that can be produced with a planar process. So Purdue has a long history engaged in this field. Yes. Is it supposed to be larger than the source? It doesn't have to be. They're usually kind of symmetric. There's nothing fundamental that usually differentiates the drain from the source in these devices. It's the bias you put on it. So how do we actually manufacture these? We said there's this integrated circuit thing. We could kind of do something with it. Well, the starting point is a silicon wafer. You start with a silicon wafer. These days, 12-inch, 300 millimeters is standard. And you start then processing. And one of the things that makes it work is you can do massively parallel processing. You don't make one chip at a time. If you're trying to make a microprocessor or a GPU chip or whatever it is, you don't make one chip at a time. You process a whole wafer full of chips. And the way these fabs work, you actually process wafer by wafer by wafer by wafer, so you pump a lot of them through. And so you can actually get relatively high volumes of things this way. So we mentioned this planar process. The simple way to think about it is if you start with a simple silicon wafer in this case. Silicon is the semiconductor of choice. And it's got a silicon dioxide layer in the top. Silicon's a semiconductor. Silicon dioxide's an insulator. You first would deposit something on it, say the silicon dioxide. You would coat it with a photoresist. A photoresist is just a photoactive chemical that will change its properties once it's exposed to light. And the specific property we're really concerned with here is solubility. We want to either make something that is normally insoluble that becomes soluble, or something was normally soluble become insoluble. Switch its solubility. Solubility is just how well it dissolves in some chemical developer. We then use a photomask. We do a photolithography step where we have a photomask, and I'll tell you up front it's not really in intimate contact with the wafer, but just conceptually it's there. So we have a pattern. We've made a pattern on the photomask by maybe starting with a CAD program, turning that CAD layout into actually a series of squares and rectangles and other patterns on a mask. We then expose, we shine light through it, an illumination source that, as is mentioned today, is extreme UV, but traditionally we'd think of as just an ultraviolet exposure source. It's not actually the sun. We don't actually take these out into the sunlight. We actually have a controlled exposure source. It's a little bit more sophisticated, but anyhow. And then we developed the resist. Remember, we said the whole point with the resist was that we wanted to change it from being soluble to insoluble. So in this case, the regions that were exposed to light change their characteristics, and now we can actually develop away regions of photoresist that correspond to that pattern on the mask. So we've transferred the pattern from a mask into the photoresist. So we're halfway there. So the next thing we want to do is transfer that pattern from the photoresist into the wafer. In this case, it's especially that silicon dioxide layer. So now we put it into an etching system that will selectively etch the silicon dioxide much faster than it etches either the photoresist or the P-type wafer. And we actually etch, I don't know if you can see the contrast there, but we just etched an opening in the silicon dioxide where we originally had the mask pattern. So we've transferred from the mask to the photoresist, from the photoresist into the silicon dioxide. Now the photoresist has done its job, so we strip that off. And we now have a patterned silicon dioxide layer. We now do additional processes. We want to introduce the dopants we mentioned that would change the conductivity. We now do something like an ion implantation, simply fling ions at the substrate at some high energy. Some of those will penetrate actually into the P-type silicon wafer. Others will be stuck in the silicon dioxide layer. And so now we've selectively put this dopant in that region that we opened up in the silicon dioxide. Okay? What's it?
What effect does that have? Like putting the dopant in?
Remember we said we could change the conductivity of the silicon by orders of magnitude by putting impurities in? That's that part. It's also changed it, by the way, from P-type to N-type. So we haven't talked about what that means yet, but we changed the sign of the silicon, electrical conductivity, to put it simply. Yes? Because we have to transfer the pattern into this inorganic layer. So remember, the mask is, say, a piece of glass. You've got a physical glass or quartz substrate there. In reality, it's way away. We go through projection lenses and stuff. But even if it's a simple idea, the mask is actually a piece of glass, a sheet of glass, basically, with some chrome on it or something. So we couldn't get these arsenic ions through that piece of glass, is the simple answer. Okay. So the next thing we want to do is actually put metal down and deposit it. So we're going to first, in this case, deposit metal. So we're going to do kind of a blanket deposition of metal. We have ways of scattering down a thin metal layer. Notice that in this case, we want the metal to cover everything, including down into those openings we had in the silicon dioxide. We want to then pattern it. We're going to pattern it with another photoresist process. That's a pretty fundamental thing. We have these sort of cycles where we have this photoresist process with a specific mask. We then use that to transfer the pattern. And in this case, we're going to use a different mask. We don't want to use the same mask we had before. We have a different mask now with a different set of openings. We now have opened some regions in the photoresist. We want to now do an etch of that metal. So the metal region needs to get etched. So now we've transferred, again, a pattern from a mask into a photoresist, from the photoresist into a metal. The photoresist has done its job. We strip that off. And now we have at least a simple cross-section of this device we said. We now have something where we've at least patterned. We had that N-type silicon. We have this channel region in the middle. We have that oxide. We have a metal here that can be our gate, a metal here that can be our source, a metal here that can be our drain. This is very simplified compared to that cross-sectional view we showed, but I think it's a useful thing to be thinking about. Okay, so as I said, nowadays you process 300 millimeter wafers. They're the size of dinner plates, and you get a lot of chips. If you actually look on this wafer, you can see all these squares here. Each of these squares is a chip. You would fabricate all the way through the process, which could involve thousands of steps. And then you would cut this up into these squares that could eventually be your die or your chips. You would buy a microcontroller, microprocessor, GPU, whatever it is. And in the process of doing this, you wind up putting down lots of interconnects. Remember we said there would be miles of interconnects on a given wafer or given chip. You do that by successive processes where you build up what are effectively like expressway overpasses. You'll have, north-south, east-west, north-south, east-west, successively crossing over each other. Yes?
What's the
Why is it not square? Why is the wafer round and not square? You got an answer?
The silicon's growing to like a pool. I forget the name of the process.
It's a bool, yeah. It's like a big bologna if you ever go to the deli counter at the grocery store. It's grown that way. And then you cut it. You slice it into these wafers. The other argument is you don't want square corners because square corners are brittle. So you actually would prefer to process around around wafers. So you're willing to deal with, you notice you have some edges here that are wasted, but you're willing to deal with that because of those two effects we just said. Yeah.
What type of metal do they use in between? Like, what type of metal do they use in the outside? Is it like quite a bit of metal? You know what?
Well, in this particular example, there's two answers. What do we put on the silicon to make the contact is one answer. But once you get under that metal stack we talked about, this multi-layer metal stack, that's copper. Use copper for that. Okay, so to finish this thought, you process a full wafer, then you cut it into many die. So this happens to be a die that's an AMD processor from 12, 15 years ago. This is actually a quad core processor. It's actually got 4 processors on here. These blue regions here are kind of the memory blocks, and then there's 1, 2, 3, 4 processors on this chip. So this would be a quad core processor, but that's a die that's cut out of the full wafer once it's done. Okay, so I want to skip ahead to something. We'll do some other things next week. I'll be back again next week. So there's something called Moore's Law. Gordon Moore was a co-founder of Intel. He made an observation in the early 70s that it looked like the number of transistors on a chip was doubling every couple of years, every few years. This became known as Moore's Law. The amazing part is when Moore first observed it, we were going from like 12 to 24 to 48 to 100 transistors. That's when he first observed this. We were at the level of 100 transistors. So Gordon Moore made this observation that while it looks like the number of die on a chip is going up every so often, by 2019, a typical chip was about 5 billion transistors at a cost of about a penny per 100,000 transistors. And this is what's been broadly known as Moore's Law. So in 2023, Gordon Moore passed away, which was the end of, I guess, his lifetime, but not the end of Moore's Law scaling. But where we are right now, this is going on. This is a log scale. So you're doubling every couple of years, 2 or 3 years. This has been going on for 50 years. And since this is a log scale, that means this is an exponential growth. So the industry has been growing exponentially for 50 years in terms of how many transistors you can put onto a device. This is what's led to the fact that we all carry powerful devices with us on our phones and our tablets, on our laptops, GPUs. They're all very powerful, right? But where are we right now? So right now, we're at the point where state-of-the-art integrated circuits have tens of billions of transistors. Let's say between 10 and 50 billion transistors on a current state-of-the-art chip. I looked it up today. I think a Apple A15 or A16 chip. Anybody have an A15 chip in their iPhone? Anybody know what the chip is in your iPhone? A few people. iPhone 14-ish. Anybody that speak better language? 15 billion transistors on the processor of that. Okay. So we're going to do an exercise here. We got 10 minutes left. I got the 10-minute sign. I need 3 volunteers. So I first need somebody who's not going to be an ECE major. Right here. Please come up. Come on. Okay, now I need somebody who will be an ECE major. How about I don't know, how about in the back there? You're the guy with the guitar amp. Okay. And then I need one more. Anybody here not in engineering? Yeah, come on up. Okay. So here's your assignment. You 3, introduce yourself briefly. Tell the class who you are.
I'm Rosie. Do I need to give any specific information?
Just say who you are.
I'm Rosie.
On Maddox.
My name's Melinda.
Excellent. So here you go. You 3 are going to work together, okay? So here's the question you're going to answer. How many transistors are in this room? Go ahead. You can use the board. You can poll the audience, phone a friend, ask an expert.
Well, iPhone's right.
Yeah, so we got about, let's say, 150 people in the room. Okay, so 150 people. Here you go. We'll get you started. 150 people. 150 people.
Yeah.
Times.
Okay.
So feel free to poll the audience, phone a friend, whatever you need to do, okay?
What do we do, like average? Like,
Usually no, in those, they're just metal.
Do you need the audience? You need to poll the audience? All right, they need some information from the audience here.
Difficult to say because
Oh, okay, got it.
GPU or CPU.
So I guess we need the amount of people who have different devices, and then also we don't know the amount of transistors on average that each of these have. So
Yeah, but we've got some simple math here. So assume edge CPU's 10 billion transistors. So anybody's carrying a smartphone, tablet, laptop, 10 billion transistors per CPU. And then you got to find out how much memory they have, okay?
okay.
The numbers are just unbelievable. The worst is we just toss them. In like a couple of years, one of those complex things we make. And it's just
Hey, if you brought a computer, raise your hand. All right, and now if your computer does not have a GPU, put your hand down. Which means if it has a GPU, keep your hand up.
So we have 140 students in the class.
Every time I've done this, somebody in the audience second guesses the experts at the front of the room.
Gone on. I need a new laptop now. Yeah, maybe I should get one of these framework ones. They've got a pretty good review, and you can swap out the motherboards and stuff. They were designed for that. So. I don't mind it, but I don't like the lag when they quickly check whether you're allowed to run a program or not with the Apple. The grip Apple has on the computer is too much. In fact, I went to Linux Windows 11, I think, when Microsoft uploaded my stuff to OneDrive without asking for me. I was like, yeah, this really isn't my laptop anymore, is it? I mean, you let me think it is, maybe, but it isn't. But Apple's kind of worse. But at least I feel Apple's more upfront with the way these tell you do want to be Apple. So he just preserves it with the holding it wrong.
And then just use that as a sample size for the rest of the room. 15 people, since there's 150 people in the room, that's 10%.
Are we close to an answer? 2 minutes?
So, because that's a sample size, that's 10%. So pick like a letter. If somebody's name starts with a letter, C. That's good. Almost.
Okay, guys.
Guys, we have a solution.
All right, let's go.
So everyone, so we have too many people to know how many people have like on average a certain amount. So what we're gonna do is we're just gonna take 15 people and see who has like an iPad or watch, and then like we're gonna go from there. So like, who in this room?
Just say like, stand up if your name like starts with the letter C. Okay. And then maybe like
R?
R. Okay, wait. Okay, what's this?
You can come up with a bound.
We need like a 5.
Data set is what?
So we did 15.
Yeah, but I mean like
All right, you guys got 2 minutes. Take your best shot.
Now from here, how about we start like on this side? So,
Just do the math. Do the math on what you have.
okay.
Do the math on what you have. So, assume everybody's got everything.
Okay, I assume everybody's got
Assume
it.
everybody's got a laptop with a GPU. Assume everybody's got an iPhone.
Okay,
Just
got
do
it.
that math.
Got it.
So,
Okay, while the experts are coming up with an answer here, we need to talk about what's going on. So if I get everyone's attention for a minute.
you think everyone has iPad?
So 2 important things while we're waiting for the expert answer.
Everyone has iPad? Everyone has calculator? I don't think everyone has calculator.
First of all, there's no right answer to this question. Even if we did a week-long study with everybody's device and figured out exactly what you have, we would be missing things. Because you can look up how many transistors an Apple A16 processor has, but then we'd have to drill down to everything else everybody has, and so we'd always miss something. So we're going to come up with the best estimate. As engineers, sometimes we need to know if the answer is 10 to the 15th or 10 to the 20th, so we can work this out. The other part of this experiment that is interesting is the fact how we ask for volunteers. So why did I ask for those 3 volunteers the way I did? Yes.
So you can get a wide
Maybe like,
The answer is so we get a different set of perspectives, different skill set, different people might bring different things. But why is it relevant to the semiconductor industry? Oh, why? Answer?
Because there's a lot of different fields that are involved to like engineering.
There are a lot of different aspects to the semiconductor industry. The industry hires people across a range of engineering disciplines. It hires people outside of engineering. It brings in people that think about supply chain management, scheduling. So there's a lot of opportunities. We'll talk next week a little bit more about this. But people come into this tending to think that it's an ECE-dominated field, that the way to come into semiconductors is be an ECE. But that's not what the industry hires. They actually hire from across a range of disciplines. It depends on what segment of the industry you're going into. But the industry needs people from every field of engineering and most other disciplines on campus. And before everybody has to leave to go to dinner, because the dorms don't serve, everybody's hungry.
okay, we'll change.
You guys got an answer for us?
Okay. A watch. And then maybe your headphones have like 5. Wait, no, we're only doing 3. Oh, we're only doing 6? Okay, is that good?
So best answer in 30 seconds.
Maybe like,
Guys, if I want to spitball, I say we just get 600 million.
maybe like 1 trillion.
Huh?
600 million.
I say if we're spitballing, I say we bet about 600 million.
Okay, we have an answer. The puff of white smoke has gone up on the smokestack over a wall. We have a final answer. Before we all adjourn, the answer is, grab the mic, tell us the answer.
All right, so we tried to be scientific about it, but near the end, we kind of had to spitball. I suggested that there are just about 600 billion transistors in the room right now. Huh?
So our
Like 1,000?
our experts are consulting for a moment. Please give us one more moment.
It's probably like... Oh, God. You might be right. It's probably going to be more than that.
Okay, so if I get everyone's attention for just a moment before we adjourn, we're rechecking the math up here. I think the number is safely in the tens of trillions. Our expert from the industry tells me I've been way too conservative. The number you would like is? Certainly north of 100 trillion.
Does anybody have memory in their computer? Okay. And that memory is made of NAND flash, right? And for every bit of NAND flash, I need how many transistors? Well, 1. This one has 8 terabytes. That's 8 trillion transistors in here just for the memory, right?
So the key is that these devices are everywhere. So we think about the transistor count on a CPU. We also have to include flash memory, your solid state hard drive. There's tons and tons of places we have to think about. So transistors are literally everywhere. So we need to adjourn for today so you can all get off to dinner and stuff. Thank you very much. We'll be back again next week. Thank you.